Welcome back. We're going to be talking right now about these forms of energy and the energy balance. And the energy, well, is the ability of a system to perform work, which in other words is work that is going to be stored. We don't really care for the total energy of the system. Rather, we care about its changes. And when a system is changing energy, it's because a work has been performed. You might remember from physics that you have kinetic energy, potential energy such as gravitational, elastic, electric, magnetic, and the internal energy. These were concepts seen in physics previously. The kinetic energy results from the motion of a body and is given as 1/2 of mv squared. If you want the kinetic energy that is specific, is 1/2 of v squared. And this is a car moving, right? And this gravitational potential energy is the energy that results from the elevation of a body in a gravitational field. And it's mgh. The specific one is gh. The internal energy is the sum of the microscopic energies: molecular translation, rotation, electron translation, molecular vibration, electron spin, nuclear spin, sensible and latent energy due to kinetic energy for the molecules, chemical energy due to the atomic bonds, chemical reactions, nuclear energy due to bonds within the nucleus, fission and fusion reactions. So the total energy that is going to be contained is going to be equal to the kinetic energy, potential energy, and the internal energy. This is, of course, if we don't take into account magnetic, electric, and some surface tension effects. This is energies that are going to be content, but energy can also be transferred. In order to transfer the energy that is going to be transferred to the surroundings or from the surroundings, then it's going to be heat, and heat is when the driving force is temperature. But if the driving force is another one, such as pressure or voltage for the electric one, is work, what we talk about. There is a kind of work which is the flow work, which is P times V, is due to the motion of this. This is a fluid that is flowing, and this motion is having this workflow, PV. The Thermodynamics First Law states that energy cannot be created nor destroyed during a process. It can only change its form. And it gives rise to this energy balance that we're talking about. The net change in the total energy of the system during the process is equal to the difference between the total energy entering and the energy leaving the system during a process. Any balance states that inputs minus outputs plus production minus consumption is equal to accumulation. Remember that. And the production and consumption terms are going to be very, very important when we talk about chemical reactions. But really right now, we're not going to talk about that. We're going to talk about that later. So inputs is going to be equal to outputs. Internal energy plus kinetic energy plus potential energy plus this work of flow plus heat plus work that is going to be entering the system minus what is going to go out of the system is going to be equal to the change in energy. Now, important, U plus work of flow, we can state that is enthalpy. Enthalpy is a convenient combination of these two properties, U plus PV. So we can add them up and have H plus kinetic energy plus potential energy plus heat plus work entering minus this going out is going to be equal to a change in energy. If there is a steady state and no chemical reaction, the accumulation of energy is zero, which means that we're going to be having just these situations, H plus kinetic energy plus potential energy plus heat plus work in minus the ones out is going to be equal to zero. Once again, if the system is a stationary system, in a closed system with velocity and elevation where its center of gravity remains constant, then this is going to be canceling kinetic and potential terms. So enthalpy plus heat plus work entering minus heat plus minus enthalpy plus heat plus work going out is going to be equal to zero. So this is in terms of enthalpy, which is very important. So the change in enthalpy is going to be equal to M integral from T1 to T2 Cp dt. When the temperature is changing, this Cp is the heat capacity at constant pressure, and it's depending on this temperature, and it's going to be obtained from a table. So you have to do an integral, and this is going to yield to a fourth grade equation that depends on temperature. So this is about it, and we're going to be seeing in class many exercises about this so that you can get acquainted. Sometimes it is important to have one temperature, which is the temperature of reference, and then we can say that that H is going to be equal to 0, and we do the integration from that temperature of reference to another temperature, but the rest is just to do delta H. So that's the reference temperature, and it's going to be very important later on where we talk about phase change and chemical reactions. That is everything about that. Thank you very much. See you later.